So we're going to be having a look at relational databases and graph databases, and there's a lot of material talking about sort of the differences between these and how they're alike. So we thought what would be interesting would be if we take like a data set and do a worked example on it, showing how you might approach the problem with your. So we're making the assumption that you've already got familiarity with relational databases, and maybe graphs are a bit newer. But we'll have a look at how would you go approach a problem, and how you can still apply your relational knowledge to the graph, and which bits are different. So this is the rough structure of what we're going to do. So I guess we're going to go for a little bit under an hour. So we'll have a look at the data set. We'll have a look a bit at modeling. How do we do modeling in the graph and relational domains? How do we import data? How do we check the data that we've imported is actually okay? Obviously, probably most interestingly, how do we go about querying, and how does that compare to what we do in SQL? And along the way, we'll look at how we migrate or refactor our model. So our data set is one which is obviously going to be a bit divisive. So it's a favorite of mine. So I'm a bit of a football fan of watching football. There's a website called Transfer Market that has a bunch of the football transfers. So for those of you who are not familiar with the domain, effectively there are football players, and they play for a team or a club, and they can be transferred from one club to another one. That's effectively the domain that we're going to work with. So you can see on the screen now, it shows some of the top transfers from, I think it's from the 2015 transfer window. And the data, so I scraped the data, and you effectively get it in a CSV type format. But you can imagine this could be a dump from Hadoop, or it could be, I suppose it could be a dump from another a relational database if we had it in there. But here I've got it from a third party. And what we've got, sorry, trying to move the control panel out of the way so I can see, but it keeps on doing that. So we've got the player information on here, so it shows what season did the transfer happen in. So you can see these ones go back quite a long way. So they've been tracking, or they've got the transfer data going back, what's that, like 27 years. And so you see there's a bunch of player information. There's an ID for us to represent the player. If we go on to the next slide, you can see that we've got a selling club. So that's the team that owns the player at the beginning of the transfer, and we've got information about the club. Again, we've got another identifying URI, and we've got the country they're from. And then on the other side of the transfer, we've got the buying club, and so they're the ones who are purchasing the player. So we've got the player, we've got the selling club, we've got the buying club, so it's kind of three pieces of data. And then finally, we've got the transfer itself. So this is like the transaction where the player goes from team 1 to team 2. So how would we go about modeling that? So let's have a look at a relational approach. So this is one model. I'm sure if you're playing along at home, you can think of another way that we can model it. But this one seemed to me like the most obvious way that I would go about solving this. So I thought there kind of seemed to be three types of data. So we've got some players. So on the left-hand side, so we make a players table, and we'll put an ID, a name, and then which position they're playing in. Then in the middle, we've got the transfer. So those are like the transactions of the players, and we put in all the information there. And that one would have a foreign key player ID connecting to the primary key ID in our players table, and then it has another two foreign keys from and to club ID, which point to our clubs table on the right-hand side. So we've got three tables. The graph equivalent of that is pretty similar. So I guess the easiest possible way when you're looking at relational databases and graphs is you can just do a direct mapping of your where your foreign and primary keys are into what we call a relationship. So I'll go through what each of these pieces of the diagram mean, but this is what it looks like. This is like the completed first model that we're going to do. So this is the pieces of terminology. So there are only 4 pieces of terminology that you need to remember to get started with graphs. So the first thing is we've got nodes, and those are, so we've got them highlighted in red on this slide. And they're representing, in this case, the player, the transfer, and then the club. And you can think of those as being equivalent to a record or a row in a relational database. And in this case, they map directly to the table. So you'd have a player node would be a row in the player table. A transfer node would be a row in the transfer table. So those are nodes, and we usually use those to store our big data items. So those are where most of our data is going to live. We then have relationships that are connecting them together. So you can see those are now highlighted, and we've got one going from transfer to player, and then we've got other ones going from transfers to the club. And you might notice they've got different. The ones going to the clubs have different names because they're representing different relationships. So for the one on the top is saying, well, this is the club that the player went from, whereas the one underneath is saying, well, actually, this is where the player went to. So they mean completely different things. What else is in? I'm trying to think. What else can we say about this? So this, yeah, the only thing to keep in mind is that this is the equivalent of the join in our relational model. So where we had those primary and foreign key on the diagram, that join is only calculated when you execute your query. Whereas in a graph, on this diagram, these relationships are actually stored in the database. They're stored on the disk, and then they're stored in memory when queries are running. And so you pay a slight write penalty to write those relationships at the time when you're creating your data. But then when you query it, the idea is that it's already computed, so you're not going and computing how things are joined later on. And so the underlying idea is that if you've got queries that are using lots of relationships or very connected domains, then a graph is going to work very well for you. We've also got properties. So these are the key values that just sort of hanging off the edge of each of our nodes. So for the player, we've got a name and a position. For the transfer, we've got a fee and a year. And then we haven't got it highlighted, but on the of player relationship, we've also identified what age the player was when that transfer happened. And so that's a property as well. So you can put properties on nodes, and you can put properties on relationships as well. They're used to store attributes or metadata. For relationships, they can sometimes be used to store a weight or a quality of a relationship, depending on the domain. Although in this case, we don't have those particular use cases. And our final piece of terminology is we've got the labels, and so those are used to group the nodes. So where we had a player, transfer, and club node, the bit now highlighted in red, the text in the middle, that's like a category, if you like, saying this node is of type player or of label player, and the one in the middle is of label transfer. So that's our model. So we've gone through what we've got. So we've done nodes, so those are the pieces of data. We've done labels, those are how we group them or categorize them. We've got relationships connecting everything together, and then properties are indicating what data we have on each of our components. So if we could do a side-by-side comparison, just so you can just see what's another way of looking at the difference between the relational and graph models. So on the left-hand side, we've got the relational one, and you've got the data is in tables or relations, and everything's very structured. So you define up front, these are the fields that I have. And we can have what you could call soft relationships. So there are relationships in there, but they're not actually stored in the relational database. They're computed when we query. Whereas on the right-hand side, we've got our graph model, and you'll see the nodes are not all uniform. So just because two nodes have the same label, so for example, imagine two nodes both have the person label, it doesn't mean they have to have all the same properties, and it also doesn't mean they have to have all the same relationships going out. So they have a bit more flexibility around it. And then we'll have, and then the relationships here are actually stored. So we'll call them, these are hard relationships, or they're like pre-computed relationships, if you like. Okay, so that's the model. So at the moment, we've done models are pretty much the same. Next step is how do we get the data into here? So for the relational one, we need to make sure we define our schema. So we've got to go and get our players table set up. I'll go through the first few examples of this a bit more slowly and explain it, and then we'll go quicker as we get on because they're all effectively repeating the same pattern. But we're creating our players table. We've got a primary key. We've got a name and a position. Then we want to go and generate some insert statements. I'm sure for some relational databases there are tools that we could use to load this in bulk, but this was the quickest way that I knew how to get the data in. So I generated a load of insert statements and loaded in some of the players. Then we do the same for the clubs. So we've got to create the clubs table, load in the data for the clubs. Then obviously the next thing is we've got to create the transfers table. Again here, note that we've got three foreign key, primary key relationships going on down the end, connecting us into the players and clubs tables. And then we insert the transfers as well. And that's it. So that's right. So that's our mod. So relational, it's create the schema, import the data. With the graph, we're going to use. There are lots of tools for getting data into Neo4j. We're going to use one called Load CSV, which comes with Neo4j when you download it. This is built into the query language, which we'll talk about in a second. Used for importing sort of small to medium-sized data sets, so up to about 10 million. Your frustration levels with how long it's taking will probably be fine. The idea with how this works is that it is running the load CSV transaction through the Neo4j transactional engines. There are other tools for doing bulk loading of data sets, which will skip the transactional layer, but this one does transactions for while you're importing. And the structure looks a bit like this, and we'll go through this as well. So the first bit is we're going to say I want to load a CSV file. You can optionally say that it's got headers. In this case, we know that it's got headers because we had the first row indicating what each column means. And you can point it either at a file or you can point it at a HTTP URI if you want. We then basically just iterate over that file or HTTP link, and we get each record in that file. And we could either match. So match is our way of looking up something. So saying I want to match a pattern, so go and find me something. Obviously, that wouldn't be very interesting if the database is completely empty, but if you were doing an update, that might be a good place to start. We might say we're going to create something, so we're going to use the create command, or we can use a command called merge, and merge will create it, but only if it doesn't already exist. And so that's quite useful here because there's lots of duplicate data in our CSV files. For example, clubs will appear multiple times because they participate in multiple transfers. We can also use it to explore the data. So here's an example of me looking at one of the transfers CSV files that I created. So we say I want to load CSV with headers from the transfers file, and then we're just saying I want to count how many rows there are. So we're not actually looking at it yet. This is the 6,500 transfers. So I'd taken the transfers off. They give you the top 100 for each season. So I just grabbed those. We can also use it to go and have a look and see what does one row of this CSV file look like. So you probably already know if you've done any data work before, you've probably gone and had a look at that in your favorite text editor. But it's also nice to just see that Neo4j is processing it correctly. So what we can do here is see what's it going to look like in Neo4j land when we try and load this file. What you get back, you can see on the right-hand side, we get key values telling us. So basically, it takes the column that we had on the first row and then maps it to the value that in this case is on the second row of the file, and you get pairs. So for example, if we look at one of them, we've got the seller club country is Portugal, and then if we go down the end, the player name is Aldair, and it does it the same for every column. What we want to do now is go and create the players. So the most obvious way to do that would be, well, okay, we'll just adapt that load CSV command from the previous slide, and we'll fill in a create command instead. So what we're doing here is we're saying I want to create a player. So in this case, it means a node with a player label on. So that's the colon player bit. And then we'll put 3 properties in. So we've got the ID pulling out the player URI. We've got the name pulling out the player name, and the position pulling out the player position. This is fine if you've got no data in, but you've got to be a bit careful. And probably a better first step is actually to go and put some constraints on the database. This is often the first thing that people do with Neo4j. They don't realize that it will let you do whatever you want by default. There's no constraints on it at all. You don't have to go and create a schema like we did with the relational database. You basically you've got a lot of freedom, although obviously with that comes quite a lot of responsibility as well, if you like. So in this case, we're going to restrain ourselves a bit to make sure we don't mess up our data set, and we'll create a constraint on player. And what we're going to say here is that the ID needs to be unique. And what this will do is if we try to run it again, for example, it will say, no, I can't do that because you're conflicting with a record that already exists. So you can think that this putting this constraint on is reasonably similar to what you'd be able to achieve in a relational database if you were using a primary key, for example, and you didn't want to end up with 2 rows that were representing the same thing. So we're achieving that goal here. But even better than the disadvantage with once you've got that unique constraint and you use create is that as soon as it conflicts, it will just exit, and then that will be the end of the transaction, and it obviously won't do anything. It will just roll it all back. So what we really want to do when we're importing something is use this merge command, and what this will do instead, we'll say, okay, well, I'm going to check if it's there. If it is, cool, I'll just skip on to the next row. If it's not, then I'm going to create it. So merge is like the combination of looking something up and creating it. So it's like idempotent creating, if you like. So it only creates it once. We'll do right for the clubs. We're a bit more aware of what we need to do. So we'll create the ID first. We'll get our club ID in there. And then we'll do the same thing. Because the clubs are a bit spread out, so there's some that are in, some will appear only in the seller club rows, and some will only appear in the buyer club rows if they didn't do a to and from transfers. Then we'll do two statements to do that. So we'll do one that creates the selling clubs and one that creates the buying clubs. And then we'll load that data in. And then finally we can do the transfers. So we'll make sure we don't create duplicate transfers first. And then we'll load in our transfers. This is quite, so now we're using a match clause, because for the transfers we want to go remember from the model, we want to connect the transfers to players and clubs. So we've got to go and look up the players and clubs that we're going to connect to. So we do that first. We go and find all the players, find the clubs, and then after we've done that, we'll make sure the transfer exists. So again, we'll use our merge command to create the transfers. So you can merge on, so we can merge on nodes. So we did that in the previous slide. So we're doing that again here. We're also using a command called onCreateSet, and it does reasonably what you might imagine. So it's saying if when I'm executing this merge command, the node is not already there, then go and set these properties. If it is already there, just ignore me and go on to the next part of the query. And finally, we're using the merge to merge some relationships. So you can use the merge for creating nodes or for creating relationships. And what we're doing here is saying, I want to merge the off-player relationship, so make sure there's an off-player relationship from this transfer. Make sure the transfer identifies the from club, and also make sure it identifies the to club. And then we're also setting the player's age on the off-player. So that's it. And so then once we've done that, we'll have the data in the database. And I think at this point I'll just do a quickly show you what it looks like once it's in Neo4j, and then we'll go and look at how we'll do some actual queries. So this, if you've not used Neo4j before, this is what we call the Neo4j browser, and this is like I suppose the entry point where you can go and write ad hoc queries or create stuff in your database. It's a developer tool for browsing around and seeing what's in the database. And if we have a look on here, so I just clicked on the little green cylindrical type item on the top. We get a bit of an overview of what's in our database. So we can see we've got some labels, and there's clubs, and we've got countries and players. I've cheated a bit because I've scared. This is the data set from the end of the presentation, so some of these will be unfamiliar. But for example, we've got clubs, and we can click on there, and it will. Maybe I'll make that a bit bigger. So you can see here it's loaded in. It's actually executed a query for us, and we'll go into the syntax of these queries in a sec. And it's showed us 25 clubs. We could also view them in a table view if we wanted to. If we didn't want the visualization, and it will show you the node and the properties on there. You could also get a text view if you preferred that. And if you're sort of at the point where you want to go and build an application with this stuff, and you want to see what actually happens when you execute this query, you can also have a look at what's going on under the covers as well. This is probably not such an interesting view, but if you're curious, you can always check it out. We can also do the same for the relationship, so we could go and click on that from club one there, and it will create us a little graph of the from club transfers that have happened. You can download it, so we could get an export, so we could get a PNG of this diagram if we liked it. We could get a CSV export as well. You can make this full screen, so we could put a full screen on there, and we can sort of browse around. And if you click on something, it will open up the nodes that are surrounding it, and you see that might not have been such a good one. So Brazil, there's lots of transfers of players that are from Brazil, so that one's, you see that's loaded up lots of stuff. So let's go back to the slides again. So I'm just going to run the clear command. So you see when you type things in here, you'll get it'll autocomplete to help you out. And we're just going to clear the screen, and we'll come back in here again in a second. But let's have just a quick talk about how Schema works. So for the relational database one, you'll remember we created all our schema up front, and for the graph database one, it was letting us just put whatever data we wanted in until we put some constraints on. So in Neo4j, there are 4 types of constraints that you can do at the moment, but these are often evolving. So if you come back on a future edition, there might be some more added in. But at the moment, there are 4 main ones. So there are unique node property constraints, node property existence constraints, relationship property existence constraints, and the newest one are node keys. So let's have a quick look at what they do. So we're not going to use all of those in our example, but it's good to know what they do. So this one we've seen already. So this is just making sure we've got a unique node property constraint. And the way it works is we're saying I'm going to correct. So this one we did already. So we're saying I want a constraint on the label club. So every time you see a node with the label club, make sure the ID is unique. If you did a node without the label club and you had duplicate IDs, that's fine. It won't prevent you doing that. It's only restricted to those nodes that have the club label. We can also ensure a node property exists. So in this case, we could say, if you create a node which has the club label, then it's got to have a name property. And if you try to create a club without it, then we're going to reject that statement. So that's reasonably fine. We can do the same for the relationship property. So we might want to say, when you create that off-player relationship, I need there to be an age property on it. So we can do the same thing there. And then the newest one, so these are node keys. So this is the equivalent of the composite key, if you're familiar with relational databases. What we could say here is, on any club, I want the node key to be the name and the country. So those two combined have to be unique, and neither of them can be empty or missing. In this case, it kind of does almost the combination of the key and the existence. Okay, so hopefully those map up with some of the things that you can do in a relational database. Now we're going to have a look at the two query languages. So we've cheated a bit and we've done a bit of Cypher already, but let's have a look at how it would compare to SQL. So we're going to start really simple. So the first queries will be very easy, and then we'll build them up. So the first thing we might want to do is we want to say I want to find a player by name. So one table scan, find one record. So select star from players, where player's name Cristiano Ronaldo. The equivalent of that, so we're going to use our match clause. So remember, match is for finding things. What are we finding in this case? We're finding a node that has a player label and has a name property that is Cristiano Ronaldo. So we match that player and we return them. So easy enough. The equivalent parts of the query, the from and where, effectively map up with that match. In Cypher, so this is the Neo4j query now. It's a Neo4j implements Cypher, but it's also if you look up Open Cypher, you can see there's lots of other people implementing it as well. But we're doing this is syntactic sugar for saying a match where clause, and when the query planner takes it, it actually explodes it out, and it would look pretty similar to the SQL one. And then the only other thing that's perhaps the other way around, if you come from a SQL background, is that where we indicate what we want to return is at the bottom of the query rather than at the top. So in SQL land, we'd say I want to select, and then we list what we wanted to get back. Whereas in the Cypher query, we do that at the end of the query. So we write the whole query, and then we say I want to return these things. So that's just a slight subtlety. And if we run the query, we'd get back a row representing Cristiano Ronaldo. So let's do something a bit more interesting. So what happens if we want to find transfers between two clubs? So remember, any transfer has a from club and a to club. At this time, we're saying I want to find transfers from Tottenham to Manchester United. So this is what it would look like in SQL. So we've got some joins in here that we didn't have in the previous query. So we're starting from the transfers table, and then we're finding we're joining the from club, and we join the to club, and then we join the players. This is the Cypher equivalent. And we'll just have a quick look which bits of the queries map to each other. So the match here is equivalent to those joins in there, and I'll just go with my mouse so you can see which one each one maps to. So join clubs as club from, that would be this bit here. So this is that join, if you like. The club 2 is over here on the right hand side, and then the player one is here. So you'll notice that where we have to write, every time we want to join in a new table in SQL, we have to go and write a new join clause and work out which properties or which fields did we use in each one to map to each other. In the Cypher equivalent, we just join, we just sort of do a little arrow coming out of the node, and we point it at the place where we want to go. And then, yeah, the other bit is that the select and the return are still the same as before, and you'll notice here we've exploded out the where clause instead of doing it in line. You can do either. Their performance equivalent. The only reason I've pulled it out here is because it makes it easier to read on the slide. if you prefer to do it inline, you can do that. Equally, if you prefer to do it in the fuller format, that's fine as well. And if we were to run that query, we can see we get back some results. This one's a bit more interesting to see. So I've in my Neo4j browser, I've actually saved some queries where we've got those transfers. So if I click on here, you can see there aren't actually any transfers from Tottenham to Manchester United in this transfer window. So I've changed the query a bit. So I've gone for Chelsea this time, and you can see there's only one transfer. But with these, it's quite easy to go and change it. So if we decide actually I don't really care where the player comes from, just show me all the transfers that went to Manchester United. By the way, now you've got there's no prizes for guessing which team I support. But we could then say we could show who was coming into there, and we could also show where they came from. Equally, if we're being fair, we could say, okay, let's have a look who Chelsea have got, and it will show you those players. We could do some order by, so we could say actually show me them by the transfer fee in descending order. I think it was already doing that. Don't know if it was doing it for all of them, but we could go back to this one and we could say do this one ordered by transfer.numeric fee, and you can sort of play around with this. This is sort of like a playground for sort of having a look at what's in the database, and we could mess around with any of these. So if we wanted to just say, can you show me the transfer of one player, we could go and inline that in here, and it will just come up with just that one transfer. So if we just wanted to see, maybe we wanted to see where did Nemanja Matic go from and to, then we could do that. Or maybe if we're following the news a bit, we say, okay, if I've forgotten where did Neymar go from and to, and oh, okay, he went from Barcelona to Paris Saint-Germain. You can see this is quite an extortionate amount of money. It's 199 million pounds. So this is what you can do. So this is quite nice. So we can kind of play around with this in here. I'm going to go back again, back to the slides to just do a quick explanation of something else in our model. But hopefully you can see so far. So it's not too difficult to write these queries in Cypher that do the same thing as what we do in a relational database, and it's not very hard if you want to slightly change the query. It's reasonably easy to do that as well. If we decide actually I don't really care about the from club, or I don't really care about the to club, or actually I don't care what the from or to clubs are. What I care about is the player. It's really easy to go and change the query to do that. Another common thing people think about when they're doing starting to work with graph databases, they wonder how do indexes work. So I know in relational databases how they work. So if I've got a table and I'm doing some joins on it, I probably want to make sure there's an index on there so that when it's scanning to do my join, it's not doing a full table scan. I want to get my indexes on there, but I don't want to do too many indexes because then it takes up a lot of space. The way to look at how the indexes work in the two models is that in the relational one, we're using it to do our index scans, and then we're effectively doing sets, sort of joining to each other, and we're trying to find the intersection. And so indexes can often speed up your queries. On the graph side, I think the easiest way to think about it is that is these blue nodes on here, and these are the starting points of our query. And indexes are only used for those, and then after that, you're effectively using what you could think of as there's like pre-computed indexes between the nodes that have relationships connecting them together, and effectively you're just jumping around those node pointers. So there's no indexes involved after the initial find me my starting points. So what's the starting point? So on our previous queries, in query number 1, Cristiano Ronaldo would have been the starting point. It was also the ending point, so there was no actual real query after the starting point. In our second query, the starting points would have been the two clubs. So we had Tottenham and we had Manchester United, or when we ran it in the browser, we had Chelsea and Manchester United. And so we had two starting points there, and then we could go and try and find out how those two nodes were connected via that. Well, we were giving a very particular structure to look for. How can you tell? So the next question is, how do I know if I'm actually using indexes in my query? So when you run a query, you can prefix it with a keyword. There's two. There's explain or there's profile. Explain will go and tell you what the statistics of the database think the query plan will look like if you execute it. And profile will actually go and run it, and then it will give you back the plan that it actually came up with. And what you're looking for to see what indexes we used is you're looking for the operator node index seek, which indicates I used an index to seek this node. So I would have found a node using it. And if we read this one, it's saying it only used an index to look up the Manchester United node, and then it just went on and used the graph to find the rest. If you happen to know, like maybe you know a bit better than the compiler, and you're like, actually, I really want you to use an index for the from node as well, you could put in a using index syntax in the query, but we're not going to go into more detail on that, but just so you know that it does exist. Next question is what can you index then for these looking for these start nodes? So you can do equality. So we've been doing equality searches. So we've matched like player names, or we've matched club names. You can also do starts with, contains, ends with. You can do range searches on numbers, and you can check for non-existence. The next thing we're going to look at is another common thing that people wonder when they're like trying to transfer their relational database knowledge into the graph world, and it's how do I migrate the model? So migrating a model in a relational world is often a bit of a job, isn't it? And you've got to work out, make sure you don't mess up the existing application, and make sure it's still normalized and it's still correctly able to perform for the queries that you want to do. So I'm just going to have a look at a migration of this model. So with this data set, one mistake that I made was I forgot that I had player nationality as well. I just didn't import that. And so I thought this would be a good chance to try out a bit of a migration. So we've got an extra column, so player nationality, and we want to add it in. So we'll start with the relational one. So it's not a complicated migration. We'll do a bit more of a complicated one in just a minute. So all we're doing is adding a nationality field to the players table. Okay, so reasonably simple. So step one, we've got to alter the table. So we've got to alter that players table, add the nationality column in, and then we'll just run some queries that go and find the nationality and update all of our records. So update players, set the nationality to a particular value where the player ID matches an existing ID. So easy enough. So again, the two parts, so schema, then data. The graph model, same thing. So we're not going to do anything fancy yet. We're just going to add in a new nationality property onto our player. And this time we can do it in, again, we can do the schema and the data together. So we'll go back to our transfers file, we'll look up the player, and we'll use, in this case, just the set command. So we're saying for every player you find, I definitely want to set the nationality to the value from the transfer file. That's it. So we've now got the nationality of players into the database, which allows us to find the transfers of only English players going only from English clubs. So I suppose this one could now be dubbed the Brexit means Brexit query, if you're into your politics. Again, it's quite similar to our previous query. So just the where clause is a little bit different. But in Cypherland, we've also got a bit of a different where clause, and in this case, we're just matching England over and over again. So I'm sure if you're used to your normal forms, you were thinking, oh no, we've got that nationality, that country is duplicated in lots of places, and you can see that in the query. So we could have a quick look at that one. So that I can see if we can run that one in here as well. So these are the transfers for this transfer window. So these are only English players, or players whose nationality is English going from an English club to an English club, and we could equally change that, and we could say it's a bit of typing, so we could say, okay, I've got to find Spanish, so get me all these are Spanish players going from Spanish clubs to Spanish clubs. I could say maybe I want to know, are there any Italian players going from? No Italian players going from. What about Italian players going from Italian clubs to Italian clubs? Yeah, so you can see there are some of those. We could say, and again, you can mess around with this and say, "Oh, just show me all the transfers involving Italian players." So these are all the transfers involving Italian players, regardless of whether or not there was two Italian clubs involved. So you can see on the fifth row here. So I just highlight it. That's a player going from an Italian club to an English club, and then the line below is going to a Spanish club. But we'll get into a bit more detail on that in a sec. So I'm just going to scoot back to the slides again. And on the database that I've got running on my laptop, I've got just the transfer window of this year. But on the one on the screenshots from, this was pulling in the top 100 transfers for the last 25 years. And so you can see you get some slightly different results, but again, it's the same concept. It's all players in from England going from an English team to an English team. Next thing we might want to do is we realize actually we could add in a whole load of countries. So we've got like country data and we've got nationality data. It'd be cool if we could do some country or confederation transfers. So for those of you not familiar with football, the country bit I guess is reasonably self-explanatory. It's just which country did the player represent. The confederation is perhaps more unfamiliar, and so the idea here is these are taken from the World Cup qualifying region. So these are where countries, which confederation a country belongs to for the sake of qualifying for the World Cup. That happens every 4 years. And so you can see there's UEFA, so that's the one that gets all the European countries. We've got OFC, that's getting all the countries in Oceania, and then there's other ones for the different other continents or regions. And so we want to bring those in. So we want to do a bit more migration. This one is a lot more complicated than the previous one we did. So if I go from the left-hand side, so where we had nationality, we're going to get rid of that, and we're going to replace it with the country ID foreign key, and that's going to map over, so if you follow the red line across, over to a countries table, so that's over where my cursor is now, and we're going to create a new countries table. We're going to connect that countries table via a foreign key federation ID into a confederations table, so that's a new one as well, and that's got a bunch of information. And then finally, we're going to replace the country column in the clubs table with a country ID. So we're bringing in 2 country IDs, and then we're mapping them into these new tables. So same sort of thing, create our confederations table, import the confederations, create a countries table, insert the countries. Now it gets a bit more interesting, so we've got to go and adjust our clubs table to add in a country ID, and then we've got to do an update statement on the existing clubs table to go and map it to those club IDs. And we'll end up, so at the moment we've got a bit of duplication, so we've got country United States and country ID USA. We'll then drop it, so we'll drop the country column. Then we'll do the same for players, so we're going to add in the country ID to the players table. Again, we'll update it. This is an update command. I think I don't know if this is, I was using Postgres, but I'm not sure that this is Postgres specific or not. And then we do the country ID, and that's the same sort of thing. So we've still got a bit of duplication on the right-hand side of the screen. But now we'll drop the nationality because we don't need it anymore. When you're doing your application, you've probably got this as part of a migration process where you move the application and the data at the same time, and you wouldn't want to drop the nationality if you were using it on your application somewhere. Let's have a look at the graph equivalent. So when we're doing the equivalent of migrations, it tends to, the terminology you'll see is refactoring the graph rather than migrating it, but you can consider those 2 words equivalent. And again, we're going to be introducing a new country node, a new confederation node, and then we're going to put in some relationships connecting the players to the countries and clubs to countries. How do we get that data in? Same sort of approach as we did before. So we'll load CSV and we'll get the confederations in. Then we will do the countries. So we'll connect, and we'll also connect the countries to confederations. So that's this bit down here. So it's looking up the confederation that we created on the previous slide, merging in the country, and then connecting them to the confederation. Refactoring the clubs we'll do that all in one go. So we'll create the new part of relationship from club to country, and we'll remove the country property. And then we'll do the same for players. So we'll create the new place for relationship, and we'll delete the nationality. So if you remember before, this was our query to find the transfers of English players, and it was quite we were repeating England lots of times, and we thought, can we get rid of that? So yes, we can. So this is the new version of the query that makes use of those new relationships, and in the relational one, so we've got 3 more joins in there because we've got to join in so now that country is its own concept, we've got to go and join the country tables in. So we do it 3 times, one for the from country, one for the to country, and one for the player country. And then on the graph one, we've got extra relationships. So we've added in the place for relationship and the to part of relationships. One thing you'll notice is different is that in the relational one, we still have to say, well, the from country join, or that join is England, and the to country join is also England, and the player country is also England. In the graph one, we don't need to do that because we can use, so if we just use the same variable name everywhere, so in this case country, so we've got country here and country here, they're all referring to the same thing, and then the where clause is saying what does it refer to, and in this case it's saying well, it's England. And so we could take this, so I've already got this new model in our graph over here as well, so we could run the same query and we get back a similar result as before. And so we could change this again. We say, show me the transfers of Spanish players. I try to think if we've got any other. Let's have a look. What other country? Or pick a random country. So if we just do, we could just find. Let's find another country to put in there. Oh, Canada. Angelica will be happy. So we'll do Canada. So there's some. Oh, they're all transfers for 0 though. That's not very interesting. I'm not sure any. I don't know. Oh, maybe we could do some Argentinian transfers, and then we'll go back to the slides again. So we could go and say find all the. So these are players who are from Argentina going between 2 Argentinian clubs. In this case, if we decided actually I only want the country that they're from to be Argentina, and I don't care what countries they're going between, we'll just delete that, and then it will do that. So now it's finding Argentinian players that went from any club to any club. So by removing the variable here, so we call this an anonymous node. So we're saying there's a node there, but I don't care about it because I'm not going to use it elsewhere in my query. So we're just saying they need to be part of a country. I suppose that actually in this case we could probably just get rid of that part of the query completely, and it wouldn't make any difference. Okay, but that leads us on to our most fun query of all, which is transfers between different confederations. So remember, a confederation. Transfer is of a player and of a club. A club is part of a country is part of a confederation. So we've got a bit of a mini hierarchy going on, which means that if we want to find confederations, we've got to do a whole load of new joins. We've got to bring in, again, we've got the countries coming in, but we've got to join those countries to their confederations. So we've got some extra joins in here. For the graph one, we can do quite a nice thing because we use the same relationship names. We use the relationship name part of. So we said a club is part of a country, and a country is part of a confederation. We can actually use what we call a variable path search here. So you can see where we've got the *2. That's saying I want you to follow a part of relationship for what we call 2 hops. So normally when we're just defining a relationship type, it's just saying, okay, I'll just go and look at the end of this relationship, what's there. In this case, we're saying I want you to go and look 2 levels. So go from the from club, go to what's at the end of that part of relationship, and then do another one. And you can change that number to whatever you want. So if you've got, for example, an organizational hierarchy or a product catalog, you could say, okay, just go and look all the way down and find me what's at the end. Although in this case, we've specified it's 2 because we know what the structure is. And this allows us to find the transfers from one confederation or one sort of continent to another one. So I've got a few more which are not on the slides on this one, which are quite fun. So we can say. So in here we're saying I want to find all the players that are going from South America to Europe. So we could run that one. We can see, so these are transfers that happened this year. So these are players going from clubs in South America to clubs in Europe. So maybe you recognize some of these names. What we can also do is we could track the money flow. So we could see where is the money going to. So I'll just put this in full screen so I can just explain what I've changed. So the confederations are still capturing those, but I'm not restricting them to a particular one. So I'm just saying there's a confederation there, but they shouldn't be the same. So we're trying to see where's the money flowing from and to. And so if we put it in here, so this is showing on the left-hand side, you've got that's where the money's going from, and on the right-hand side, this is where it's going to. So if we just see this number here, so there was 259 million went from clubs in the UEFA, so that's in Europe, to AFC, so that would include China and Australia. And then equally there was 205 million that went from South America to Europe. This is obviously because we've said they're not the same confederation, it's actually not finding the biggest spend, which is from UEFA to UEFA. So that's European clubs to European, and that was for this year, so 2017, 2.1 billion pounds has been spent on transfers going between those between clubs in those regions. And then if you scroll down, there's some of them there haven't been any monetary transfers between these ones. Some of these, and obviously there are some really massive transfers that happen that really skew some of these numbers. But we could also, so what we're doing here, we're doing a sum. So we're saying, tell me how much was the total of the expenditure. We could also say, tell me how many there were. So there were 3,400 transfers from UEFA to UEFA. And we could then, if we wanted to continue, we could then go and say, okay, find me the average transfer fee, or find me we could do the max. The max is quite a nice one. So we could say, show me the max transfer fee that happened between those two. So this is the Neymar one we looked at before. So we've got 199 million transfer there. The maximum for UEFA to Asia. I think this is a player called Oscar, so it's 54 million, and then you can see the numbers get a bit more sane as you go down the screen. Okay, so if we go back here again, so one of the nice things that's really easy to do once we've got it in a graph, so we can do that money flow transfer really nicely. So that's the end of the querying section. Now we're going to have a quick look. So if you wanted to see what's in the database after I've done the import, how can I translate my relational tools to the graph world? So this is Postgres specific, but there are equivalent commands for MySQL or for Oracle or for SQL Server. If I wanted to list the tables, so I want to see what my schema is, I could do a command like this. If I want to do the same thing in the graph, the equivalent of that is the labels. And you remember on the top of the Neo4j browser, we had the node labels up in the top left-hand side. We can also call a procedure. So we could call db.labels. So if we just typed in that text, it will show us what labels we've put on things. And they're pulling out the equivalent of all the tables. If we wanted to see what actual properties have you got on there, we could do that in a relational database for our countries table. Our equivalent in the graph world is having a look at the indexes. So we could do the indexes and we could do the constraints by calling the appropriate procedures. You could also run a query to get back the keys that are on particular nodes. So in this case, we're saying, find me the countries and then get the keys. So keys will give you what properties are on a country and tell me how many times does that occur. So remember that just because two things are a country, it doesn't mean they have to have the same properties. So we might get a difference. In this case, we don't. But for this one, we do. So for clubs, I got a difference. So I got one which still has a country attached to it, which we'll get to in a minute, and then we'll see why is there one that still has a country attached. Another common thing that people like to do is do an entity relationship diagram. So I can do that quite easily in Postgres, and I can see how my tables are related to each other. So my countries connects to my confederations, connects to my clubs. That goes back to transfers, which also goes to players. There's a procedure that does that as well. So this will create you a graph of the graph, if you like. So we've got a call DB schema, and it will give you back a diagram of what your underlying data looks like. So you can see we've got player going to transfers, transfers going to clubs, clubs to confederations, and then countries, countries into clubs and confederations. How do we check our data integrity? So we've done a little bit of that with the constraints. But we can also do some afterwards. We might want to check did our refactoring actually work, or migration, did it work? So here I'm looking at which countries are where is the country ID still null despite having migrated it, and this pulled out South Korea and Ivory Coast, and it was because in my two data sets they referred to countries as a different thing. So in one it was Korea South, in the other it was South Korea, and in one it was Cote d'Ivoire, and in the other it was Ivory Coast. So that was reasonably. I just had to go fix the data there. But if you've done stuff with data before, I'm sure that's a well-known but a bit arduous task that you're familiar with. This is the equivalent of how we would find those rows in our graph query. So we just say we're going to do a not. We're going to do a not relationship here. So we're saying find me all the clubs where there's not a part of relationship going out. And again, it pulls out that unknown record. It also pulls out Monaco. So I don't know if there's anyone from Monaco on here, but listening in. But on the data set where you say what does Monaco map to, it says Monaco the club is in Monaco the country. And so obviously you might choose, depending on how contentious you want to be, you might say, well, actually, I'm going to say Monaco's in France for the sake of my data model, but it just purely according to what the Wikipedia dataset says, it actually says that Monaco is actually in Monaco. So we end up with the club Monaco doesn't have a country to link to. The unknown one, I guess you would have to decide what you want to do with that. So it would be fine to leave it in there, like it's not violating anything by being there, but it wouldn't come up in any queries where we did a part of relationship, for example. How do we delete data? So it's pretty similar in that respect. So if we said, I want to go and drop the countries, we might run a drop table countries, and it will go, you can't do that. There's some other tables relying on you. We'd have the same thing in Cyphers. If I tried to go and delete the countries, it will say it's just a different exception type, but it's saying, you can't do that. It's still got relationships attached. But what you can do instead is there's a detach delete command that will allow you to take it deletes a node and it deletes every relationship attached to it as well. And I've reached the end. I'm probably a bit early, so we've probably got a bit of time for questions. But my TLDR of the whole talk is, if we're coming into this graph world, we're now dealing with some different terminology. So we've got nodes, relationships, properties, and labels, but I'm sure you've already remembered that because we went over that at the beginning. If you want to do easy import of CSV files, which is obviously we can get relational databases into that quite quickly, and it's quite a common format in a lot of APIs. We can use the load CSV command to do that. By default, there's no constraints. So if you're wondering, how come it's just letting me put any data I want in there? That's what you would expect when you start. The schema evolves as we import the data, and probably you go and put constraints on at some point. And hopefully you've seen from the example that this model is the way that you model stuff in a graph is quite easy to evolve and refactor, and we find it works quite well with when you're doing sort of an agile project where you don't really know what exactly you want to build at the beginning, but you work it out over time. And now I will pass back to Angelica.
Thank you so much, Mark, for that great presentation. Hopefully everyone enjoyed it. So we do have a couple minutes left. So I'll read out a few of the questions that you guys posted in the GoToWebinar panel, and I'll leave it to Mark to answer. So someone's asking, can I migrate all SQL databases into Neo4j?
Yeah, so we've got a tool. Let me show you this one. So there's a tool which I guess we can send out afterwards, can't we? So if you've already got database you've already got data in graph database, we've got this tool called Neo4j ETL components, and this one will take. Try to see, we've got the names of it on here somewhere. So these are the ones that it supports. So we've got MySQL, it's got Postgres, it's got Oracle, and then SQL Server. And this is at the moment an offline sort of import. So you can see here we can export the data into a CSV format, and then we can import it and back in again. And it uses an offline tool called Neo4j import, which takes it's a very particular structure of CSV files. It's a little bit different than the one that we were using, but then it will create you like an offline database that you can then obviously start up your Neo4j instance and use that. But if you were doing ongoing like importing data across, you probably you wouldn't want to use that one.
Great. So does it make sense to have mandatory relations on nodes that shouldn't be able to be deleted? And if so, is that supported? So the question is around access control in general.
Okay, yeah, so for access control, I can show you how that works if I just browse to that. So we do role-based role-based access control, saying action. So there's a blog post here which we can obviously send a link to. So these are the roles so that users can have. So when I was logged in, I was just admin, so I had access to do anything. But you can create users and give them different access. So for example, we could say this person, we could give Angelica access to my football database. Probably wouldn't be that interested in my football database, I imagine, but if you did, I could give you a reader role, and then you would only be able to query it. We also allow you to create, you can kind of do completely locked down roles, so you can create new roles, and you could then say that role only has access to procedures, and you could control access to very, very fine-grained data through a procedure. So you could say they can only execute this procedure, and inside your procedure, you could write the code that says, oh, I'm only going to explore this particular bit of the graph that this user is allowed to touch. So an obvious example, or an example of that would be, let's say we've got a HR database, and maybe we say it's fine for everyone to see a list of all the employees and what office they're working from, but we don't want them to be able to see the salary unless they are the HR, for example. And so maybe we create a procedure that allows you just to see the information of the employees, but you can't actually, if you went to the database, you wouldn't be able to just write a random query. You'd have a procedure that controls what queries you can run on it. Hopefully that answered that to some degree at least.
Yeah. I guess we have time for another one. So it's easy to see the advantages of using a graph database during the R&D phase of a project, as the schema can evolve more easily, but in your opinion, would a relational database be faster and more efficient in the production phase?
So I think it depends on what the actual data looks like. So I'm sure there are certainly domains where which are really optimized for doing relational database type querying, but from the work that I've done with our customers, we've sometimes seen people actually have a relational database in the field. So they've done all their R&D on the relational database, and they've got that in production, and then they find there are certain queries, or maybe they want to introduce a new feature, and they're not able to get the query to run quick enough on the relational database. You're probably right. In the data set that we're using today, there's not enough data in there to probably see much difference between the two models. But once you start loading lots of data in and you have lots of joins or lots of relationships going on, you'll start to see a difference. And one that I did quite early on when I was getting into graphs versus relational was with a customer of Neo's called Shuttle, who were then acquired by eBay 3 or 4 years ago, and they were trying to do a query that would find out which delivery company could take an order for one of their e-commerce customers. And they wanted to be able to show the user lots of different slots. So if I wanted to get same-day delivery, I can choose, I'll have it between 1 and 2, or 2 and 3, or 3 and 4. And they found that to get just one, like on their relational database query, just to get one slot to say, hey, this slot is available, it was taking 2 seconds. And they wanted to show you 40 slots. So on average, it was like 80 seconds to generate all those slots for you. And I think their favorite quote was that once they moved this over to using a graph, or using Cypher to calculate what slots were available, their slowest delivery slowest delivery took longer than their, so the end-to-end using Neo4j to get it to someone's house was quicker than the slowest query took. So they had one query that would sometimes take like up to 10 or 11 minutes to run. And that was combining, so it's like look up an order, find the from sort of locality, find the to locality, check whether or not it fits into the car or the bike or the lorry, and then give it back to the user. Well, effectively like it in like real time in quotes, so where they're sort of on a web page waiting for the response. So yeah, there are certainly, yeah. So if you've got lots of joins in your data set, lots of relationships, and those are where the queries are centered around, you're probably going to see that the graph is better. But equally, I'm sure there are ones where there are features of the relational database that is going to do better.